Hey Joel,
Yeah,
I heard you say you're gonna record this.
yeah. And am I still sharing my screen?
Yeah, I can see everything. I'm in a lot of pain right now, and I think I might
I'm gonna-
jump off of here if you're recording it.
Sounds good. Sorry to hear that.
It's okay. We'll see you later.
Okay. So hypothesis testing, what do you guys understand from hypothesis testing? If you watch that video, what was, for the first example, that first one, what were they considering? What was the hypothesis they were testing for that problem? It was related to Shakespeare. Um, so someone discovered a new poem from Shakespeare, a new sonnet. I think it was a sonnet. I don't know. And what was the big question there? Say again. Is it written? Yeah. Did he write it or not? And how did they think about testing this, right? How do you test if a poem is authentic? What was the method they were using? There's a certain metric. What was that? Unique words, right? So unique, I think new, right? So they have like this baseline vocabulary from Shakespeare, and they found that in each poem there was a mean of 7 new words in each poem. So that was going to be their metric. Is that the real way to determine? I don't know, but it's a data analysis method to do that. So in this new poem, they found that there were 10 new words for this new poem. So, and on average, there's a mean of 7. So the hypothesis in this case is that we'll assume that it's a Shakespearean poem, and we'll try to prove that it's not by seeing is 10 new words. Is this really different from 7? And when we say really different, there's a lot of baggage here. How do we tell if it's really different? We kind of go to our statistical analysis, right? Another way to say that is this is a mouthful, it's really hard for me to say, statistically significantly different. And this is where we do we can compare means using a t-test for small samples and population or population variance is unknown. Or we could use a z-test, which is just based on the normal distribution, and we assume that we know the population variance, or we do know it because it's been well studied or something like that. And this is based on the distribution of means. That's what we talked about for our sampling distributions last time. So that in the video, they ran you through an example. I think they assumed that the population variance was known. They had all of Shakespeare's works analyzed with all the vocabulary, and they could definitively say for each sonnet, we know the mean and variance of unique or new words in the poems, right? So they actually do have the whole population, all of Shakespeare's works. So there you go. So you can do a z-test on that. So that's the setup. That's kind of what we're doing here. And we can do two things. We can compare a single sample mean with a population mean or some other value. And in the homework, you're going to look at an example where I give you data from Cadbury egg shipments, inspired by our recent Easter holiday. And you're going to say, well, nominally, I think it's the weight of these eggs is 5 grams. Here's a distribution of egg weights. And is our mean value from our sample different from this nominal weight, right? There's going to be some variability in the manufacturing process. Is it different than this kind of certain number, right? So with the population mean or some other value we care to test for. And then in that second video, you looked at comparing two means. From two samples. So X bar 1 is that equal to or greater than or less than X bar 2? And in this case, this would be X bar is equal to, we'll just say mu, or X bar is equal to some number. So let's walk through this hypothesis testing process and look at how we actually accomplish this. What do you think the first step we should take when we are doing a hypothesis test? What should that be? We're going to think about what we're asking, right? And what are we going to test? So we want to just state our hypotheses. State hypotheses. So what are the two hypotheses that we're going to evaluate? We learned about the null hypothesis. So H sub naught, null hypothesis. And usually this is just that something is the same as something else. Because usually you're testing, is there a difference, right? So null hypothesis, and I'm going to switch examples here because I like this one a little bit better. Our experiment is going to be, does holding a puppy make people happy? I think it's a really important experiment. And how would we do this? We could evaluate someone's level of happiness, 1 through 10, have them hold a puppy for 5 minutes, 2 minutes. I don't know how long holding a puppy, what that duration should be, because if you hold it too long, it probably ends up not being enjoyable. Maybe just like be in the presence of a puppy. So we'll say 5 minutes, and then we have them do the survey again, okay? Did we increase their happiness level? So what would my null hypothesis be for this experiment? I'll ask Gerald. Holding a puppy. So null hypothesis would be, it's kind of like the baseline. So null hypothesis would be holding a puppy does not change happiness. Score, we'll say, and score happiness. All right, so we have the happiness score before. So we'll say X bar happy pre. And X bar happy post puppy. All right, so this is essentially what we're saying. They're essentially equal. We can't say that they're different or not. So that's our null hypothesis. Our alternative hypothesis is what Gerald said, and we'll call this alternative hypothesis, is that holding a puppy, what do you think, increases or decreases? Depends on how big of a cat person you are. I'm going to say increases. We could also test if, does it change your happiness level, right? In this case, we're going to say H bar happy pre is less than X bar happy post puppy. This is also known as a one-sided test because we think that our hypothesis is that our happiness after is going to be greater, right? So it's a one-sided test. We could also say X bar pre is not equal to X bar post, and this would be a two-sided test. Because it could be greater than or less than. And there's a important change in how we do the analysis based on that. All right. So we stated our alternative hypothesis and our null hypothesis. So here's the actual hypothesis right here. For HA. And then here is our hypothesis for our null. Okay, so we'll do our experiment and we'll test this. Step 1. All right, let's go to step 2. Now we need to identify what kind of test statistic are we going to use. And this basically is our population variance, known or not. Sometimes this might be stated, sometimes this might be assumed. In this case, this is a new study, it's cutting edge psychology here. We don't really know the population of happiness in people holding puppies. So we're gonna say that we'll assume that it's unknown. And if we assume that it's unknown, what kind of test statistic or test are we gonna conduct? Z or T? Z is based on normal, T is based on the student's T distribution. The T distribution, because that's for small sample sizes or unknown t-test, unknown population variance. All right, so we're going to use the t-test. If we did say, okay, you know what, we're just seeing if people holding husky puppies, this is my favorite, versus other dogs, and so this isn't cutting edge research. A lot of people have done this research, and we're just trying a new breed, and so we kind of have an idea of the population variance of people holding puppies because it's been studied for decades. Then we would use a z-test. If so, we're going to use a z-test. And our z statistic based on the population mean, or the distribution of means, is equal to X bar minus mu over sigma square root of n. In this case, our t-test is equal to x bar minus mu over sigma square root of n. But we'll get into that specifically a little more later, what that is. All right, so we've identified the test statistic that we're going to do. We could also say we could have a different alternative hypothesis, and that could be that the variances are different. Actually, that would be HA. And in this case, we would know the variability of people's happiness levels, and we would do a chi-squared test, as we introduced last time. So that's a different thing we could do, but we'll focus on the means right now. All right, so now based on sample means, we're going to calculate test statistics. We're going to go with this t distribution because we this is cutting edge research. We don't know the population information. So we take our sample. We say n is equal to 20 puppy holding sessions, and we calculate x bar. And x bar for holding puppies is equal to 7 out of 10, which is the score. And we find that our standard deviation is equal to 2. So we could do two things. We could see if there's a difference between the first, before you hold the puppy and then after you hold the puppy. We could also compare it just to the population mean of just general happiness. I'm going to write out the two things, and I got to look up one of them because I didn't write it down here. Variance. We'll stick with the one thing right now. I just don't want to mess up the two. Okay, so we're going to compare this to the population level happiness. So mu, based on research out there, we've given this happiness survey to millions of people, and on average, people are a 5. They're kind of middle of the road. So this is from our general population. We got to work on that 5. We got to up that. Maybe we need more puppies. All right, so we'll calculate our t statistics. So t is equal to x bar minus mu over s square root of s over square root of n. So x bar from our sample is 7 minus 5 all over 2 square root of 20. And we end up with a t statistic of 4.47. Okay, we're getting there. I think only 2 more steps. So calculate our t statistic. And this is just like a z-score. Remember, and a z-score tells us how far away from the mean is our observation based on the standard deviation. And so in this case, if we look at the t-distribution, which is symmetrical, we're really just asking 4.47 is how far away from the mean is this? If our mean value is 5, we've normalized everything based on the mean and standard deviation or standard error. Is this a big difference or not? And how probable is observing a value this far away from the mean? That's really what we're asking here. So let's go to the next step here. I'll leave that up. And we're going to kind of redraw that in a different way. So for step 4, we need to identify a threshold t-score or z-score beyond which we can reject the null hypothesis, H naught. So I'll just draw that t-distribution again. And we want to say, okay, well, what is the probability? So this threshold, and we'll call that threshold alpha, which is related to this. We'll call this the significance level. So alpha is it's a probability, and it refers to the area on either side if we're doing a one-sided test or a two-sided test. Alpha would be the area to this side of this particular t-score associated with that alpha value. So often we set alpha at 0.05 for 95% significance level. And for a one-sided test, we would calculate the t.95. So the t-score associated with a cumulative probability of 0.95, meaning we have, I'm just going to erase this right here for now. So this is 0.95 area, right? Leading up to that point. And this is for a one-sided test. Meaning we're in this case, we're only interested in seeing if our happiness value is greater than that mean value. If we're to do a two-sided test, it would look like this. And alpha would be still alpha is equal to 0.05. But now we have to divide it by 2 because this is 0.025 and this is 0.025. And we still have 0.95 in the middle. But now we're kind of stretching it out a little farther because we are testing on either side of this. So it actually has to be a little more extreme of a value. And we're looking at now, in this case, the t 0.975. And these values, if we do it on either side, will give us the probability of 0.95 in the middle. And this is a two-sided test. So it's, the alpha equal 0.05 is kind of like a standard. Alpha is typically going to be between 0.1 and 0.01. Depends on the application. And sometimes, you know, you don't need to prove a statistical significance. And we'll, you know, for example, if we are looking at something that's really tragic or important, like traffic fatalities or, you know, product safety kinds of things. And well, you know, if we put a stop at the, or no turn on red lights, no right turn on red light sign up here, and that reduced accidents by 5 over 3 years compared to 10 accidents over the previous 3 years. Is that a significant difference or not? Well, do we care? I mean, it reduced accidents by 5, right? Like that's pretty important. So we might not always care to do a significance test if something's really important and you kind of see a demonstrated good in a particular thing. So this isn't the be all end all is what I'm saying. So what does it mean to calculate these values? Well, you can go to the t-distribution and say, okay, if I look at the cumulative distribution function, I say, give me the t-value associated with the cumulative probability of 0.95 or 0.975. And then I can compare those t-values with my actual t-value from my data to see how they fall. So basically, if my t-value from, we'll just say x bar and s, is over here, then we fail to reject. But if it's over here, then we reject the null hypothesis. And this says that if I'm over here and I'm on the other side of that threshold value for the one-sided test, this says that the mean of my sample is so different from that population mean or whatever value I'm comparing it, that it's really unlikely, you know, I have a 95, or I only have a 5% chance or less of getting a mean that from a sample that is in fact not different from the population that I'm comparing it to. So I have a really low probability of failing or of inaccurately rejecting the null hypothesis. And that gets out to this idea of a false positive, also known as a type 1 error. And we'll talk about different types of error next week. And so alpha is whatever alpha is, and say in this case it's 0.05, I have a 5% chance of a false positive, meaning I say that there is a significant difference, but in fact there isn't. I inaccurately reject the null hypothesis. The way to think about this from a false positive perspective is, say I'm doing some kind of test, like a medical test. And medical tests, as we know, COVID tests, right? Depending on the kind of test we're doing, it has a certain accuracy associated with it. And so how often am I going to say you have COVID when in fact you don't, right? The concentration of COVID RNA in your blood is over this point, the significant threshold point, and we say you have COVID, but in fact, it's just an anomaly and you don't. So that's what a false positive is. And you can set that threshold depending on how important it is to not have a false positive. All right, so now our last step is we're going to, we can compare our t-score from our sample to the T score based on alpha. And for a one-sided test, this is going to be T1 minus alpha. And for a two-sided test, this is going to be T1 minus alpha over 2. If you're doing a z-score, the z is always going to be the same. So for alpha is equal to 0.05, T 0.95 is always going to be equal 1.64. Pretty sure, let me just double check before we etch that into stone. Because the normal distribution isn't a function of your sample size, but the T distribution is. So 0.95. Yeah, 1.64. And then for alpha is equal to 0.05. And for two-sided, we're doing T 0.975. That is usually 1.76, but let me just double check. 975. Oh, 1.96, sorry. Yeah, there was something up there. 1.96. So those are, sorry, gosh, guys. Z. But again, this is only for your known population variance. And those are going to be constants, but when we're dealing with T, this is a function of n. Also, which is your degrees of freedom, right, is related to that. Okay, so in degrees of freedom is equal to n minus 1. So now we can just compare our scores. So in this case, we did our one-sided t-test. So we're testing the alternative hypothesis is X bar puppy happiness is greater than X bar no puppy. So it's a one-sided test. We'll do T.95 with degrees of freedom equal to n minus 1. And this ends up equaling 1.73. So we can do that in R, or we could look it up in a table. In R, we would do quantile T, so QT, 0.95, we put in the probability. And then we give it the degrees of freedom, and that spits out this answer. So remember, quantile is always going to be the value of whatever distribution you're interested in. So remember that our T, X bar, and S, and N from our experiment was equal to 4.47. So 4.47 is greater than 1.73. Therefore, we can reject the null hypothesis and proudly proclaim that holding puppies increases happiness. And just again, what we did is we said, what is the t value for a one-sided test below which 0.95 of cumulative area exists? And that t value given our degrees of freedom is equal to 19 was equal to 1.73. And then our sample t statistic was way over here at 4.47. So given that statistic, we can actually calculate the probability associated with that 4.47, which is known as the p-value. So the p-value is the probability of observing x bar given n and s. Given that x bar from our experiment is actually equal to the x bar of our population that we're testing. So meaning that the null hypothesis is true. So and this gets back to the type 1 error, right? We said, okay, holding puppies makes you happy. We proved it. We got this really big t-score. It's over the threshold. But, well, there is still this small probability that, in fact, the mean from our sample is just abnormally big because we got a big sample, right? We happen to have people that are super into puppies from our sample of 20 people, but they're not really representative, right? The true population of people holding puppies is not into puppies, and the means aren't that different. So you could just have, sample variability, right? Think about doing this 10,000 times, and you're going to get different mean values each time. So there is, in this case, a small probability that, in fact, our null hypothesis is true, and we can't reject the alternative hypothesis. So what is that probability? Well, it's just, it's basically the area on this side of your t-score, right? It's just, what is this area? So to calculate that area, we're going to do we need the CDF, right? And because we're doing, what's the probability that our t from our experiment is I'll just say it this way. So it's the probability above t from our experiment. We'll just say it that way. So we'll use the cumulative probability, but because we're going above, we need to do 1 minus, right? So 1 minus the CDF, which is PT. We plug in our t statistic, 4.47. Degrees of freedom is equal to 19. And we end up with 0.0001. So very small probability, 1/10,000th of a chance. It was a really big experiment. It was groundbreaking. Everyone heralded the authors. There was a run on humane societies. No puppies went without a home. All right, so we've done this study. We're going to publish it in a journal, the Journal of Canine Psychology, and we need to report these results. And so there's a specific way we should report these results so that people understand exactly what we did and what the data really mean. So the way to report this is we can say that people holding puppies are significantly more happy than people not holding puppies. Or the general population, right? And then you report your statistics. So you can do parentheses, we'll say T19. So this is the parameter that goes into T, the T distribution is equal to 4.47. So we report our statistic, and then we say the probability associated with that is 1 times 10 to the negative 4. Alternatively, you could say P is less than 0.05, right? At at the 5% significant or 95% significance level. So this is the general format for any kind of statistical test you do. You want to report the actual test statistic and then the significance level or the p-value. This is a really small p-value, right? And that's a good thing. It means it's really different. But you could also just say, you know what, we met the threshold, we're good. Okay, let's take a break, and then I'm going to have you guys do your own hypothesis tests. Yeah. Not holding puppies. You were reading that right. But it was not written correctly. Before we get into the example, I just want to give you the equation for comparing two sample means. They give it to you in the video, but let's just give it to you again. And if we have two sample means, that means we're going to have an X bar from sample 1, S from sample 1, and an N from sample 1, right? And we'll have X bar from sample 2, an S from sample 2, and an N from sample 2. There we go. Thanks. Okay. So if we want to compare these, are these means different? Our null hypothesis is that X bar 1 is equal to X bar 2. And underlying this is if each sample, right, say it's people holding, not people happiness levels without holding puppies and then happiness levels with holding puppies. Under that is going to be some underlying population mean, people's relative happiness levels in general, and then happiness levels holding puppies that we're just taking a sample of, right? And so in this case, that would mean that there's just no difference between these two populations. Our alternatives hypothesis is that X bar 1 is not equal to X bar 2. This would be a two-sided. Or we could say X bar 1 is either less than or greater than X bar 2. So if we pick one of these, it would be one-sided. Great. So we need to calculate a t-statistic, and it's just the same process as before. But the t-statistic is a little bit different. All it is X bar 1 minus X bar 2. So the difference, right? This is our delta. Minus the difference between the underlying population means. But if our null hypothesis is that they're equal, then it means that our null hypothesis is that these are equal. And so this is just going to be 0. So we just cross that out. So we're looking at delta X bars up here, and then below we have S1 squared over N1, and then S2 squared over N2. So that's how you get your t-score, and then you move on and do the same steps as before. So let's talk about the example. And if I had my act together, I would let you collect your own data, but I will promise to make it up to you next week. You don't have to collect data, I'll give it to you, but you do get to enjoy the experiment. So the experiment is related to Chips Ahoy. How do you spell Ahoy? Okay, Chips Ahoy chocolate chip cookies. And they claim that each cookie has at least 16 chocolate chips. So the experiment is testing this hypothesis. All right. So what I want you to do is I'm going to give you the data. We took a sample of 65 cookies. 65 divided by 12, if everyone is here, would be about 6 cookies each, a little less than 6 cookies. You guys think you can handle that? Then we found that on average, we had 18.46 chips with a sample variance of 3.31. All right. So what I want you to do is first develop your hypotheses and state them. Second, calculate T and Z scores. So we'll assume, and for the Z score, we'll assume that S is equal to sigma, the population variance. In this case, we'll assume that S is not equal to sigma. So we'll do both. And you can say, well, a sample of 65, that's pretty big, so we'll say it's a good approximation of the population variance. Next, I want you to calculate the p-values for the T and Z scores. And compare to the appropriate T and Z, we'll say threshold scores. And I'll put the book up so you can look at that from the book. So we'll calculate the critical threshold value. So one-sided test. Let's say alpha is equal to 0.05. And we'll do the critical T value, so it'll be QT. Because it's one-sided, we're going to do 1 minus alpha. And then our degrees of freedom, 65 minus 1. All right. So our QT for 1 minus alpha is 1.67 for the one-sided test. For the two-sided test, and the Z values are what I gave you in the notes. So those are always going to be the same for the one and two-sided tests. But I'll just do that again. I'll do QT 1 minus alpha over 2. DF is equal to DF. I can just type DF in. And there is my alpha value. So it's 1.99 or about really 2.0. 1.998. And then for our z-scores, we'll do QZ. Wait, just do 1 minus alpha. Oh, Q norm, sorry. Q norm. So that value is 1.64 for two-sided. $1.996. $1.96. Okay, so who wants to share their hypotheses? Let's see if we can write these down. All right, let's ask Nick, what's your null hypothesis? Okay, so the null hypothesis is kind of the standard, and that means it's going to be the same. So alternative is going to be there's a difference. All right, so what would the null hypothesis be in that case? Okay, so the alternative is the thing that we're testing. So we'll say in this case, we'll say X bar is equal to mu, which is that, you know, we have 16 chips. Okay. What's the alternative hypothesis, Grace? Great, so we'll just do this. All right, so it's not 16, it's different. And this would be a two-sided test, so we'll just stick with that. Okay, what's your t-score, Nick? So the alternative is always going to be that there's a difference. Yeah, so it was like, okay, holding a puppy doesn't change anything, so it means the happiness level of the general population is going to be the same as the puppy holder population. So that means we're assuming that they're equal. We want to test if there is a difference. So the alternative always relates to something there being a difference in something. Okay, did anyone get a t-score? Okay, so that's a good question. X bars from the sample. So that was 18.46 minus mu, which is what we're testing against, and that was 16. Yeah, in this case, we're just testing against some population mean or some stated value. So this will be 18.46 minus 16 all over 3.31 divided by square root of 65. Did anyone get that value? So what is that value? 5.99. Okay. So the z-value, the z-score is going to be the same. It's just that we're comparing it against a different threshold value because this follows the normal distribution and the t follows the t distribution, right? So our critical threshold values are going to be different. Because we're doing a two-sided test, our t, it's going to be t.975. And we said that is equal to 1.998. And then z.975 is equal to 1.96. Pretty close, a little bit different. You can see that it's going to take a more extreme value to reject the null hypothesis for a t distribution because the uncertainty is greater. It's got a wider tail, right? This is a little bit of a bigger number than this. But in either case, because the variance is so low and we have a relatively high x bar, regardless of the test we use, t or z, we can say that 5.99 is greater than t.975 and z.975. Therefore, do we accept or reject the null hypothesis, Julio? We reject. We in fact have more than 16 chocolate chips. Or it's in this case, and we know it's more, but the sample is not equal to the population mean. All right, and then we can calculate that p-value associated with, we'll just do the t-score, with our degrees of freedom is equal to 64. So I'll just do that over here. We'll do we'll say it's going to be 1 minus the CDF for the t distribution. And our t-value is 5.99. And our degrees of freedom is 64. All right, so our p-value is 5 e to the negative 8. Really, really small probability that we have a type 1 error. Okay, we're over time. I am going to go home. I got to swap with Carrie, and I will jump on Zoom for office hours. We can talk about the Monte Carlo lab or anything else you guys would like to talk about. I'll be on in about probably 20 minutes, 2:45, something like that.